All right, so in 2.2, we're talking about how do we solve systems by Gauss-Jordan method, but now we're going to kind of get into matrices. I kind of did it in 2.1, but didn't just flat out show you what it would look like as a matrix. So we can solve systems through matrices. Note that a matrix is just a rectangular array of numbers enclosed by brackets. And then each number inside of the matrix is called an element. So we say the elements of a matrix. Also, we use a vertical line to separate the coefficients of the variables of a system from the constants of a system. This is the last column of the matrix, and it's called an augmented matrix. So let's say, for example, we're looking to solve this system, 3x minus 4y equals 1, and then we have 5x plus 2y equals 19. Now, if we want to write this as a matrix, then what we're going to do is, remember, it's enclosed by a bracket, right? And we're going to take the coefficients of what we're dealing with. So our x's are going to go in this column. Our y's are going to go in this column. And our constants are going to go, we'll call them k, is going to go in this last column. But to separate, we're going to use that vertical line that we were referencing. And so now the coefficient of x in the first equation is 3. So we write that here. The coefficient of x in the second equation is 5, so we write that below. And then the coefficient of y in the first equation is -4. And the coefficient of y in the second equation is 2. And then finally, our numbers on the right side of the equation, 1 and 19, go in that last column. And now we have a matrix representing this system. And really, in order to solve this system or solve this matrix, we're going to use the exact same rules that we used in 2.1. But now we can just fully use these rules as we need to. Remember what was said, right? So that we really want to eliminate the x in the second equation to the best of our ability, right? And then we also want to make that first term 1. So we want to make this 1, right? And then we want to get rid of our 5. It's in our best interest to go ahead and make this a 1 so that we can manipulate the top row and be able to eliminate this x variable. So it's really the same thing that we already did. Normally, you will not see these letters written above it. I did it for teaching purposes, right? So here we are. All right. So our first goal is going to be to make this 1. So we're going to take 1/3 of row 1 and we're going to replace it in row 1. All right. So this is one of our transformation rules. So 1/3 of 3, we know is just 1, right? And if you didn't know, just 1/3 times 3 in the calculator will give it to you. And then 1/3 of -4 would give us -4/3. And then 1/3 of 1 would give us 1/3. And then we just write what we already have for the second equation, right? So we just write that in just like we have it. All right. And then from here, remember the goal now is to eliminate this 5. And we can do that by multiplying our first equation by -5. So our first row by -5. We can add that to the second equation, and we're going to replace it in the second equation. So the first equation will remain the same, but this second equation is what's going to change. Now, some people need to see this step, and you feel free to write it out. I typically don't, just because it becomes confusing. But what we're saying to do is to multiply the top equation by -5. So that'll be -5. And then -4/3 times -5 becomes I believe that's positive 20 over 3, right? So if I'm just writing them as equations, and then 1 over 3 times negative 5 becomes negative 5 over 3. And so then we have 5x plus 2y equals 19. But remember, we're adding for the sake of eliminating the x term. And then what we have is 2 can be written as 6 over 3, right? Because remember, in order to add fractions, they have to have the same denominator. So if we multiply 2 times 3, we get 6. So we know we could rewrite this as 6 over 3. So when we add those two together, we would end up with 26 over 3y is equal to, and we're going to do the same thing, multiply 19 by 3. And so that'll let us know that we could rewrite this as 52 over 3. So, no, 19 times 3 is 57. So this is 57. But when we add it, then we would end up with 52 over 3. So now, that's just preliminary work. Feel free to do it on a scratch paper. But what this next matrix would look like, keep the top row, right? And then the bottom is now 0, 26 over 3, 52 over 3, right? So where we would go from here is we would go ahead and solve the bottom equation, right? It's not that hard to solve this for y. And basically, we would normally say divide by 26 over 3 on each side. But let's just say we multiply by the reciprocal. So 3 over 26 on each side. Okay, so that is what we're going to do. So this becomes, we multiply row 2 by 3 over 26. And we're going to replace it in row 2. All right, so you can feel free to pause the video and do that work yourself. But what we should come out with is 1, negative 4 over 3, and then 1 over 3, 0, 1, 2. All right. With this, if I were to rewrite this as an equation like it was initially, then this would be x minus 4 over 3y equals 1 over 3. And then remember, this is the y column, so that would be y is equal to 2. Now that I have this, I can use backward substitution, substitute that 2 in for y, and I have x minus 4 over 3 times 2 equals 1 over 3. So x minus 8 over 3 equals 1 over 3. Add 8 over 3 to each side. And we have x is equal to now 9 over 3, which simplifies to x equals 3. So now I have that my x and my y. So the solution for the system should be 3, 2. Now, this is what we're used to. This is called the echelon method. What just happened is we did it in the form of matrices. Now, Gauss-Jordan, which is what the topic says for 2.2, is when we not only take care of, putting it in the form so that we can solve it by echelon, backward substitution. But Gauss-Jordan says, hey, take it a step further. Just go ahead and solve it all so we don't have to, use this backward substitution. And so if we use this, then what's going to happen is we would continue on, right? And what does continuing look like? Well, we would take this negative 4 over 3, and now we need to make it a 0. Okay, we need to make it a 0 because in this way we would have x is equal to whatever the solution is. The same way down here at the bottom we have y is equal to 2. Right? So that's kind of the direction that we're trying to go in, okay? All right, so let's get there. So what's going to happen is we're going to multiply row 2 by 4 over 3, and we're going to add it to row 1 and replace it in row 1. That would cause this right here to be a 0. So here it is. We have 4 over 3 times row 1 plus row... No. Sorry, guys. It's going to be times row 2 plus row 1. And we're going to replace it in row 1. All right. So feel free to do your miscellaneous work on the side. Hopefully, if you've not already, you've copied down everything from the echelon method, because now we're doing Gauss-Jordan. So I'm going to erase what was done from the echelon method. All right. And we're going to do our Gauss-Jordan. All right. And so what that says is, so if we want to show the work, we can. We said that this would end up being 4 over 3. Y equals 8 over 3. So then we have, oh, I'm sorry, guys. All right, hopefully you're not completely lost. But what happens is this 4 over 3 plus negative 4 over 3 gives us a 0 in row 1. So basically, when we write this out, our second row will stay the same, 0, 1, 2, right? But our top row, what happens is this becomes 0. 4 over 3 times 2 is 8 over 3. 8 over 3 plus 1 over 3 is 9 over 3, or just 2. Am I right about that? Let's see. That's 2 times 4 over 3, which is 8 over 3, plus 1 over 3, which is 9 over 3. That's 3. All right, very good. And then from there, 0 times 4 over 3 plus 1 is just 1. So from here, what does this mean? Remember, this is the x, this is the y, this is our k. So what are we saying? We're saying 1x plus 0y equals 3. Now, we know 0y is just cancels. So x is equal to 3. And then down here, we know y is equal to 2. So that's our answer. So hopefully what you've gathered from this is once we get in this form right here, we have solved, and these are our solutions. Okay, this is called Gauss-Jordan. Solving by Gauss-Jordan instead of backward substitution. All right, but we can check by backward substitution. We can check by backward substitution. All right, so of course there are more examples that we can utilize and complete. For instance, let's say we want to use Gauss-Jordan to solve this big system of x plus 5z is equal to negative 6 plus y. And then we have 3x plus 3y equals 10 plus z. And then x plus 3y plus 2z equals 5. Doesn't that look amiss? First off, we need to know, which we haven't talked about much, but this has to be in standard form, what we call standard form. What does that mean? All of our variables need to be on one side. Variable terms need to be on the left side, and our constant terms, meaning just our numbers, need to be on the right. Right now, that's not the case. So what I'm going to do is just rewrite it so that it is the case. How do we do that? Like here, we would just add, subtract y from each side here. And what we would end up with is x minus y plus 5z equals negative 6. Now this is in proper form. So all I did was I took x plus 5z minus 6 plus y, and I subtracted y from each side. There are no like terms over here on the left side, so all I can do is just line it up in terms of alphabetical order. That's what happened. And so I did that for the first equation. I'm going to do it for the others, right? And so here, I subtract z from each side. So I have 3x plus 3y minus z equals 10. And then here, it's already the way it needs to be. So that's x plus 3y plus 2z equals 5. Okay. And so this is now in standard form. Our goal, right, if we're doing it by Gauss-Jordan, our goal is not just to have like, if we were doing it by any other method, our goal would be something like this. Like if we were doing it by backward substitution, our goal would be, let's say these are our solutions. Then it would be like, I don't know, 0, 1, some number other than 0 would be there, and then n, and then we would have 1, some number, some other number, right? And we could use the fact that we have this to solve for this, and then use both of those to solve for this. That's backward substitution. But what we're doing is Gauss-Jordan. So what Gauss-Jordan says is that we're going to make sure that we just have a diagonal of 1s, and then that will give us our solutions for x, y, and z. That way we don't have to use backward substitution. So again, this is the goal right here. Right? This is the goal. All right, so with this in mind, we're going to create our augmented matrix. All right, so that's the first step. Instead of having it as a system, let's create an augmented matrix, which we know the left side is just going to be our coefficients of our variables. The right side is going to be the constants. So right now our constants are negative 6, 10, and 5. And then our coefficients, so for x, we have 1, 3, 1. For our y, we have negative 1, 3, 3. For z, we have 5, negative 1, 2. All right, so now we've made our augmented matrix, and now comes the task, right, of first off, we want to make all these right here. We want to make those zeros. All right. And then after that, we're going to come through and see what we can do about making these zeros. And then after that, we're going to see what we can do to make these zeros. And the goal is to have the diagonals to be 1. Now, this is not necessarily an easy task, right? There is a process, and you just have to go through the process. Does it take a long time? Yes, it does. All right, but it's possible, okay? It's possible. So, one of the strategies we could use here to eliminate some things is we could take negative 3, multiply it by row 1, add it to row 2, replace it in row 2, and by doing this step alone, that would make this 3 become a 0, right? So by doing this, remember we're replacing in row 2, so that means row 1 and row 3 are going to stay the same. And then from here, this would be, let's see, negative 3 positive 3, negative 15, and then 18. And we're going to add that here. When we do that, that'll give us 6, negative 16, 28. I think that's right. So this is 0. I'm going to put that in a different color. So that's 0, 6, negative 16, and 28, right? So that's one goal, right? Accomplished. But now we need this one to be 0. So what we're going to do is let's multiply negative 1 by row 1, add it to row 3, and replace it in row 3. This is going to allow there to be a 0 in the first column for row 3. All right, so what is that result then? So we have, remember, row 1 is going to stay the same. Row 2 is going to be what we just got. And now row 3 will become 0, 4, negative 3, 11. Okay, I probably should have wrote that in red just so you know that's the one that was a result of following the rules right here. So remember what the goal is now is to get these two to be zeros. And so in order to get those zeros, that's in row 1. So that particular row would be, let's say we take row 2 plus 6 times row 1. And then replace it in row 1. Yes, because that would allow that to be 0. So we're using row 2. We know we have a 6 right here. So 6 plus negative 6 is what gives us 0. So that's why we're multiplying row 1 times 6, so that when we add these two together, we'll end up with 0, and we're going to replace it in row 1. And then for this one here, if then, this was going to be different. Okay, so 12 is what they have in common. So if we multiply row 2 by 2, and then multiply row 3 by negative 3, that'll give us opposites, and these will cancel and give us 0 here. So two things are going to happen. All right, so let me go ahead and just stick to one thing at a time. So remember, we're replacing in row 1, so that means row 2 is going to stay the same, and row 3 is going to stay the same. But our row 1 will become now 6, 0, 14, negative 8. But we have 0 here, which is great. So from here is where we're going to make this 4, 0. And we know 6 and 4 have 12 in common. So we're going to make row 2 positive and row 3 negative, so that when we add them together, we'll get 0 and replace it in row 3. All right, so here it is. We're taking again. That's going to be 2 times row 2 plus negative 3 times row 3. Replace it in row 3. And that result is So row 1 stays the same. Row 2 stays the same. And row 3 is now 0, 0, negative 23, positive 23. All right. So we do want to simplify where possible. Notice in row 1, if we divide everything by 2, that'll make that simple. If we divide everything in row 2 by 2, that'll make that more simple. And if we divide everything in row 3 by negative 23, that'll make that more simple. We want to keep it in simplest form if possible. So we're going to do 3 things at one time, okay? Again, we're going to take a half of row 1 and replace it in row 1. A half of row 2 times row 2 and replace it in row 2. And negative, basically divide by negative 3. Negative 23 in row 3 and replace it in row 3. All right, and when we do that, we're left with 3, 0, 7, negative 4, 0, 3, negative 8, 14, 0, 0, 1, negative 1. And then remember, our goal is to make these two numbers 0. So dealing with 7, if we take row 3, multiply it by negative 7, add it to row 1, replace it in row 1, we'll have what we want. So that's what we're going to do right now. Again, we're taking negative 7 times row 3, adding it to row 1, and replacing it in row 1. So that we end up with 3, 3, 0, 0, 3. And then, of course, we have 0, 3, negative 8, 14. And yes, you can do more than one operation at a time, but if you think you're going to get it confused, just stick to one operation at a time. Now we need to take care of the negative 8. So we're going to multiply 8 times row 3, add it to row 2, and replace it in row 2. And so we have now 3, 0, 0, 3. Now 0, 3, 0, 6, 0, 0, 1, negative 1. And so we want our diagonals to be 1. So we would divide I say divide, but multiply. We don't use division in matrices. So that's why we multiply by the reciprocal. So this would be 1 over 3 times row 2 and replace it in row 2. And then here we would multiply row 1 by 1 over 3 and replace it in row 1. And the result is 1, 0, 0, 1, and then 0, 1, 0, 0, 0, 1. And now that we are in this form, we have our X, we have our Y, and we have our Z. So X is 1, Y is 2, Z is negative 1. Those are our solutions. Right here. All right, that is really 2.2. If you have questions, let me know under the post or send me an email. Yeah.